This lecture is a continued discussion of probabilistic topic models. In this lecture, we're going to continue discussing probabilistic models. We're going to talk about a very simple case where we are interested in just mining one topic from one document. So in this simple setup, we are interested in analyzing one document and trying to discover just one topic. So this is the simplest case of topic modeling. The input now no longer has k, which is the number of topics, because we know there is only one topic, and the collection has only one document also. In the output, we also no longer have coverage because we assumed that the document covers this topic 100%. So the main goal is just to discover the word probabilities for this single topic, as shown here. As always, when we think about using a generative model to solve such a problem, we'll start with thinking about what kind of data we are going to model, or from what perspective we're going to model the data, or data representation. And then we're going to design a specific model for the generation of the data from our perspective, where our perspective just means we want to take a particular angle of looking at the data so that the model would have the right parameters for discovering the knowledge that we want. And then we'll be thinking about the likelihood function, or write down the likelihood function to capture more formally how likely a data point will be obtained from this model. And the likelihood function will have some parameters in the function. And then we are usually interested in estimating those parameters, for example, by maximizing the likelihood, which would lead to maximum likelihood estimator. And these estimated parameters would then become the output of the mining algorithm, which means we'll take the estimated parameters as a knowledge that we discover from the text. So let's look at these steps for this very simple case. Later we'll look at this procedure for some more complicated cases. So our data in this case is just a document, which is a sequence of words. Each word here is denoted by x sub I. Our model is a unigram language model, a word distribution that we hope to denote a topic, and that's our goal. So we will have as many parameters as many words in our vocabulary, in this case m, and for convenience we're going to use theta sub I to denote the probability of word w sub I. And obviously these theta sub i's would sum to 1. Now, what does the likelihood function look like? Well, this is just the probability of generating this whole document given such a model. Because we assume the independence in generating each word, so the probability of the document would be just a product of the probability of each word. And since some words might have repeated occurrences, so we can also rewrite this product in a different form. So in this line, we have rewritten the formula into a product over all the unique words in the vocabulary, w sub 1 through w sub m. Now this is different from the previous line, where the product is over different positions of words in the document. Now when we do this transformation, we then would need to introduce a count function here. This denotes the count of word 1 in document. And similarly, this is the count of words of m in the document, because these words might have repeated occurrences. You can also see if a word did not occur in the document, it would have a 0 count, and therefore that corresponding term would disappear. So this is a very useful form of writing down the likelihood function that we will often use later. So I want you to pay attention to this, just get familiar with this notation. It's just to change the product over all the different words in the vocabulary So in the end, of course, we'll use theta sub I to express this likelihood function, and it would look like this. Next, we're going to find the theta values or probabilities of these words that would maximize this likelihood function. So now let's take a look at the maximum likelihood estimate problem more closely. This line is copied from the previous slide. It's just our likelihood function. So our goal is to maximize this likelihood function. We will find it often easy to maximize the log likelihood instead of the original likelihood. And this is purely for mathematical convenience, because after the logarithm transformation, our function will become a sum instead of product. And we also have constraints over these probabilities. The sum makes it easier to take derivative, which is often needed for finding the optimal solution of this function. So please take a look at this sum again here. And this is a form of function that you will often see later also in more general topic models. So it's a sum over all the words in the vocabulary. And inside the sum, there is a count of a word in the document. And this is multiplied by the logarithm of a probability. So let's see how we can solve this problem. Now, at this point, the problem is purely a mathematical problem, because we're going to just find the optimal solution of a constrained maximization problem. The objective function is the likelihood function, and the constraint is that all these probabilities must sum to 1. So one way to solve the problem is to use Lagrange multiplier approach. Now, this content is beyond the scope of this course, but since Lagrange multiplier is a very useful approach, I also would like to just give a brief introduction to this for those of you who are interested. So in this approach, we will construct a Lagrange function here. And this function would combine our objective function with another term that encodes our constraint. And we introduce a Lagrange multiplier here, lambda. So it's an additional parameter. Now, the idea of this approach is just to turn the constrained optimization into, in some sense, an unconstrained optimizing problem. So now we're just interested in optimizing this Lagrange function. As you may recall from calculus, an optimal point would be achieved when the derivative is set to 0. This is a necessary condition. It's not sufficient though. So if we do that, you will see the partial derivative with respect to theta I here is equal to this. And this part comes from the derivative of the logarithm function. And this lambda is simply taken from here. And when we set it to 0, we can easily see theta sub I is related to lambda in this way. Since we know all the theta i's must sum to 1, we can plug this into this constraint here, and this would allow us to solve for lambda. And this is just a negative sum of all the counts. And this further allows us to then solve the optimization problem, eventually to find the optimal setting for theta sub I. And if you look at this formula, it turns out that it's actually very intuitive, because this is just the normalized count of these words by the document length, which is also the sum of all the counts of words in the document. So after all these maths, after all, we have just obtained something that's very intuitive, and this will be just our intuition, where we want to maximize the data by assigning as much probability mass as possible to all the observed words here. And you might also notice that this is the general result of maximum likelihood estimate. In general, the estimate will be to normalize counts, and it's just sometimes the counts have to be done in a particular way, as you will also see later. So this is basically an analytical solution to our optimization problem. In general, though, when the likelihood function is very complicated, we're not going to be able to solve the optimization problem by having a closed form formula. Instead, we have to use some numerical algorithms, and we're going to see such cases later also. So if you imagine what would we get if we use such a maximum likelihood estimator to estimate one topic for a single document D here. Let's imagine this document is a text mining paper. Now, what you might see is something that looks like this. On the top, you will see the high probability words tend to be those very common words, often functional words in English. And this will be followed by some content words that really characterize the topic well, like text mining, etc. And then in the end, you also see very small probabilities of words that are not really related to the topic, but they might be accidentally mentioned in that document. As a topic representation, you will see this is not ideal, right? Because the high probability words are functional words, they are not really characterizing the topic. So one question is, how can we get rid of such common words? Now, this is the topic of the next lecture. We're going to talk about how to use probabilistic models to somehow get rid of these common words.